Or you can talk about in your car you have a tachometer. It's usually next to the speedometer on the left. A tachometer measures rotations of your engine's crankshaft, which is connected to your wheels. The crankshaft is driven by the pistons, which are driven by the fuel exploding in the cylinders. The fuel explodes, pushes the pistons down. The pistons are attached to the crankshaft. The pistons go up and down like your legs on a bicycle, and the crankshaft is like the bike pedals, and it converts linear motion into rotations. Just like when you push your bike pedals down, that's essentially a linear motion, and that changes that linear motion to a rotation with your bike pedals. Alright? And the tachometer measures how fast in angular speed the crankshaft rotates, or you could say the bike pedals rotate in your car. So if you look at that tachometer in your car, you might see something like this. It's maybe starts at 1, and in the printed in the or on the dial of the tachometer, or the tach as we say, it says X 1000. That means these numbers are to be multiplied by 1000, and that'll give you RPM. That's revolutions per minute for your crankshaft. So 1, 2, 3. Usually it stops at around 7,000 RPM. And usually between 6 and 7 is highlighted in red, because that's what you call red line on a tach. If your crankshaft is turning say around 6,000 RPM, there's a danger of your engine exploding. So it's turning too fast basically. So you got to watch out for that, but most engines are automatically limited as to how fast they can rotate. But these stand for revolutions per minute, 1,000, 2,000, 3,000, and so on. Alright, angular speed then is defined in the following way. It's omega, that stands for angular speed, Greek letter omega. That's lowercase omega, by the way. It looks like a cursive W, I know. The uppercase omega looks like that. So we're looking at lowercase omega is equal to the angles measured over time. Angles divided by time, or angle divided by time. Angle in radians, generally speaking. Alright. Now, we can relate these two, linear speed with angular speed. So, theta is equal to S over R. Remember that? Theta equals S over R when we were talking about measuring angles on a circle other than a unit circle. Theta is equal to S over R. So that's equivalent to S is equal to R times theta. Alright? Now divide both sides of this by T, time. So you've got S over T is equal to R theta over T. Alright? Now, theta over T, remember, is equal to omega. In other words, we've got R times theta over T here. And so S over T is equal to R times omega. S over T is equal to V, right? V is angular, or rather linear measure, S over T. So this is V. V is equal to R times omega. So linear speed is equal to the radius times the angular speed, omega. Alright, let's actually use this in an example, and then we'll be done with this section. Let's find the linear speed of an Earth satellite. So an Earth satellite is in circular orbit, let's say, which is 1,200 kilometers above the Earth. Alright, so here's the Earth, and here's the satellite revolving around it in a circle. And this distance between the Earth and the satellite's orbit is 1,200 kilometers. Alright, and it makes one complete revolution every 90 minutes. One revolution every 90 minutes, or one revolution per 90 minutes. You could write it like this: one rev over 90 minutes. Alright? Now, what is the linear speed? In other words, how fast would this satellite be going if it were going in a straight line? We know it's going one revolution every 90 minutes. That's angular speed. One revolution is 360 degrees, or 2 pi radians. So it's going 2 pi radians every 90 minutes. That again is angular speed. But I want linear speed. I want to know how fast is this going if it were in a straight line. Okay? So, well, we first need to know the radius of the Earth, and we can use 6,400 kilometers for the approximate radius of the Earth. And the problem will give that to you. 6,400 approximately would be the radius of the Earth. So we can use the formula V is equal to R omega, and R here, first of all, is 6,400 plus 1,200, and that's 7,600 kilometers. Alright, so there's your radius. And omega, what's omega? We need that to get linear speed. So omega is one revolution every 90 minutes, or, well, what's one revolution? It's equal to 2 pi radians. So 2 pi every 90 minutes. That's omega. This can be simplified. Cancel the 2 with the 90, and you get pi over 45 minutes. So there's your angular speed, omega. Now we want linear speed, so we plug these into the formula. So V, or rather linear speed, is equal to R, which is 7,600 km, and multiply that by angular speed, omega, which is pi over 45 minutes. Alright, and that's equal to 7,600 pi kilometers over 45 minutes. So the answer we get will be in kilometers per minute, as you can see. This can be put into a calculator, and you can get a decimal approximation. 7,600 times pi divided by 45 is about 531. So 531 kilometers per minute. Now, if you want to change that to kilometers per hour, you would multiply by 1, 531 km over min, and then multiply that by 1, which is, make that 60 minutes divided by 1 hour. Because I want kilometers per hour, so I want to cancel out the minutes, which I will do here, and the answer will be kilometers per hour. So you would multiply 60 times 531, and the answer would be then in kilometers per hour. Alright? If you want to change kilometers to miles, you can do that too. But we won't go over that. Okay, so the homework then is in section 5.3 is 1 to 77, every other odd, and also 81 and 85. So there you go. Thanks for your attention. Have a nice day.